Good day to you, dear viewer. Today I'm going to be talking about gravity, specifically the gravitational field of the Death Star. Sir Isaac Newton developed his universal law of gravitation in the 1600s. All objects have gravity, but the force only becomes great enough to notice for very large objects. Gravity pulls objects together according to the mass of the two objects, and the force gets weaker as more separation there is between the two objects, mathematically shown here. The discovery made in the 21st century determined that channels with more likes and subscribers also pull more viewers. If you would like to contribute to my attempt at this experiment, please like and subscribe. Both objects feel this force. When the Earth pulls on you, you feel that force, and it will accelerate you quite noticeably. But when you exert the same force on the Earth, it produces negligible acceleration due to the extremely large mass of the Earth relative to the force you exert on it. You and other objects around you all exert forces on each other, but these forces produce negligible acceleration, and it is easily overcome by the other forces acting on you. To calculate force, you need to know G, Newton's gravitational constant. Back in the 1600s, Newton didn't know the exact value of his gravitational constant, but he was able to estimate it within 10% of the most recent value published in 2018. Additionally, you need to know the mass of the two objects, and you need to know the distance between the center of those two objects. Not necessarily the distance between the two object surfaces, but the distance between the two object centers. We aren't interested in the force the Death Star exerts, but rather the acceleration due to its gravity. The acceleration an object feels due to gravity is independent of that object's mass, and will only be dependent upon the Death Star's mass and the distance from the Death Star. To figure out the gravity of the Death Star, we need to know three things. The first is easy. Newton estimated his gravitational constant to be about 7 times 10 to the negative 11 meters cubed per kilogram second squared. After a few centuries, it was refined down to its current value that we use at 6.6 times 10 to the negative 11. When discussing the gravity of a planetary body, we normally look at the gravity on the surface of that planetary body. If you're standing on the surface, you're also at the radius. The radius of the Death Star is believed to be around 60 kilometers, some saying as high as 80 kilometers.
Look at him, he's heading for that small moon.
Should the Death Star have been mistaken for a moon? Well, in the solar system, there are over 200 moons or planetary satellites. If the Death Star was in our solar system, it would be around 40th in size, so it's actually above average for a moon rather than a small moon. The mass of the Death Star is a bit more complicated. We'll have to determine its mass by estimating its volume as well as its density. We know the Death Star is very close to a perfect sphere, therefore we can calculate its volume from its radius. We don't know exactly what the Death Star is made of, but I like to think it's something similar to steel, which has a density of around 8,000 kilograms per meter cubed. The Death Star has a volume of around 2 times 10 to the 15 meters cubed. For reference, this is close to the volume of the Gulf of Mexico. The Death Star has a mass of around 1.7 times 10 to the 19 kilograms, or 17 quintillion kilograms. This does assume it's a solid sphere of steel. There is, however, a lot of hollow space within the Death Star. In fact, using the second Death Star as our example of the interior, there was so much space that multiple large spacecraft could comfortably fly through it. Therefore, we can think of this mass as a large upper limit. The contrary opinion to that could be if you believe that the Death Star was made out of something significantly denser than steel. Looking at our acceleration formula, we can plug in our formula for mass. Then we can plug in our formula for volume, simplify a little bit, and now we have our formula for acceleration, which can also be thought of as the Death Star gravity. We now have our gravity formula for the Death Star and estimates for all of the necessary components. Therefore, gravity on the surface of the Death Star is about 0.13 to 0.18 meters per second squared. That's roughly 2% or less of Earth's gravity. It does raise some questions. In the scene where the Star Destroyer is damaged and seemingly falls and impacts the second Death Star, there just wasn't enough gravity from the Death Star to cause that acceleration, and therefore it must have come from the Star Destroyer itself through some form of thrust. Speaking of the second Death Star is bigger. How much bigger? Well, there's a very large range. People have estimated it to be between 80 kilometers to 450 kilometers in size. This leads to an upper estimate of gravity on the second Death Star to be as much as 1 meter per second squared. This is close to 10% of Earth's gravity, or nearly 5 times more than the first Death Star. Or at least it would have been if all the holes were closed. But it was, after all, a
fully armed and operational battle station.
Okay, now let's look at something really big. Stellar Killer Base. I mean, that's built on a planet, right? Well, it's the ice planet Ilum that has a radius of 330 kilometers. Compared to other objects in the solar system, it's more of a decently sized moon than a planet. We do have to take a guess as to the density of Star Killer Base. It could have the density of Earth as a planet, or it could have perhaps the density of Pluto, since it's supposed to be an ice planet. It could also have the density of ice, since Ilum is a planet of ice. These are all potentially equally probable. This gives us a big range, but a maximum acceleration due to gravity of 0.5 meters per second squared. This equates to roughly 5% or less of Earth's gravity. You may notice that this maximum gravity for Star Killer Base is actually less than the second Death Star. This really calls into question some of those estimates on the upper size of the second Death Star. We can look at this scene from The Force Awakens, where we can see that the Star Killer Base is clearly significantly larger than the second Death Star.
It's another Death Star.
This was the Death Star. And this is Star Killer Base.
This also makes us wonder a little bit about the Jedi. Maybe they aren't amazing gymnasts with superhuman powers. Perhaps they just do a lot of fighting and jumping on planetary bodies with very low gravity. If you like this content, please like and subscribe. Please leave a comment on what science fiction mystery you want analyzed by the StarSpace Academy.